All right. All right. Thank you, everyone, for coming this evening. Presentation tonight is regular expressions are your friend, although I like having a little bit of ambiguity on the end. Actually, I just couldn't come up with a good name, so I just tossed in several of the concepts I'll be covering tonight. So by the end of tonight, if you don't understand this, hopefully you will. So I'll show you the actual program I'm going to test. This is the string, just regular expressions are your friend, that we're going to match this against and see if it actually works and see actually how it works. So for those of you who weren't here last time, this is RxRx, which is in alpha, but it's a regular expression debugger. You can single step through things and do breakpoints and different things like that. So the first thing there, the \G right here, if I'm not blocking it, is the position of your previous match. In this case, we don't have a previous match, so the beginning is the beginning. So it's going to go ahead and match. So it's testing if a previous match assertion satisfied, because we're at the start anyway. And then this is a non-capturing group. You remember from, if you were here at the last talk, just regular parentheses, capture and group. This is a non-capturing group, so it doesn't actually put anything in $1, $2. It just groups things together. Although this is pretty pointless because I'm grouping one thing, but.
Yeah, ironically, I have to ask you to move to the right because you're blocking just the very edge of the screen there.
Okay.
They can't read the screen.
All right.
That's good right there.
I'm going to do this then. All right. So it's going to next try to match the word regular. You can see it matched. Now it's going to try to match one or more white space characters. That matched. Now this is a pretty ridiculous, don't ever do this in real life, pretty ridiculous way to match the word expressions, because this is a character set, so all of these S's are redundant. You only actually need one. But I'm specifying 11 here because that's how many characters are in the word expressions. Again, this is just for fun. And that matched. Again with white space, only this time I just did single white space instead of with the plus. Now we have a capturing group with parentheses. It's going to match the R. Then now we've got literal white space as an actual just space character. Matching a literal your, again with the white space. And then this is a positive look ahead. So it's actually called a zero width positive look ahead assertion. So what that means is, and we'll talk more about it later, but this part of it right up here says to the regular expression, I want to match whatever is in here, in this case the word friend, but it doesn't want the regular expression to consume it. It wants to verify that it's there, and then it's going to back up to the beginning of that so that the next pattern match that comes after it can actually consume it, or gives it the opportunity to do it. That one may not want to either, but it at least gives it the opportunity. Whereas in most cases, all of the rest of this, everything marked in black here has already been consumed by this regular expression. In other words, this pointer right here is past all of this stuff. You'll see what I'm saying as I step through it, if that doesn't make sense. Okay, so it's trying to match the literal friend. It matched. But now it goes, hey, we're we're going to backtrack and re-end because of the positive look-ahead assertion. And the question mark on the end makes all of this really kind of pointless anyways, because that means 0 or more occurrences. So even if I didn't have that friend down here, it would still match. But again, I just put that on there for comedic value. So now this is what is important to notice. You notice how friend is not highlighted. The pointer is now left at this position right here in the string. So that means the next regular expression, if it has \g in it, it's going to start right here. It's not going to start over at the beginning. Does that make sense to everyone? So that's the difference is, and that's why they call it 0 width. It's because it doesn't actually consume anything. The black part has a width, right? But in this case, since it didn't consume anything, it doesn't have a width. It's looking ahead of where it's matching, and it's just asserting that that value's there, and then it's backing up and saying, okay, yeah, I looked, and it's there, but I'm going to go back and allow something else to match against that later on. Does that make sense? Oh, my laser pointer died. Oh, well. All right.
What kind of battery?
I think it's like watch batteries or something. I don't know. Anyways, any questions on that before we go on? We're going to cover all those concepts throughout this whole talk. So if you didn't pick all that up the first time, that's okay, because we're going to cover all of these. So the next thing is I'm just going to cover some more of the modifiers and the combinations that I didn't cover in the first talk. I just covered the most common ones. So some people asked me about M and S and what the differences between the two were. So S I did talk about a little bit last time. So M treats a string as multiple lines, so you can have embedded new lines in it. And what it does is, instead of caret and $ matching at the beginning and the end of the string, they match at the beginning and ending of each line that's in this. You could have, like, say, a paragraph out of a book, and it'll match against the beginning and end of every line that's in that string, rather than the beginning and end of the entire string.
That's big A and little Z, right?
Yes, we'll talk about that as well. Actually, I think that's on the next slide. So S treats the string as a single line, even if it's got embedded new lines. It still treats it as if it's a single line. And it lets dot match new line, because you remember, normally dot matches anything but new line. But if you put an S modifier on there, it will match new line. So if you can combine the two, you can get a mixture of both of those things. So if you've got M and S, or S and M, doesn't matter which way you put it, it will let dot match anything, and caret and $ will match the start and end of lines. Does that make sense? Just kind of combines the two together. I only wanted to bring this up because I had a lot of people ask me about this last time. Okay, global we talked about last time, but since I'm going to be using it again, I'm putting it back in here. It just means match or substitute as many times as you possibly can, rather than just stopping at the first match. C keeps the current position after a failed match. Normally, when a regular expression fails to match against a string, it's going to reset the position at the beginning again. So C says, even if this fails, I want to keep that pointer right wherever as far as it got. And that'll make a little more sense later. I've got a full running program example of how you can actually use this in a practical way. And the two together, oh, that's good. I QC, okay. Yeah, I need a little QA, but that's supposed to be G and C. I'll fix the slides later. Yeah. So that means match as often as possible while keeping the current position after a failed match. And that's why I brought G back up again, is because I'm going to use G and C together in combination with the backslash capital G to show you how to use those three things together to do some simple, simple and complex lexing. Okay. So, again, you, you're right, Dave. We've got the word boundary. I brought that up again because I did talk about that last time, but I wanted to go ahead and cover it with an example because I think a lot of people were confused by it. So basically, the string is Doug Miles, and then I put a backslash B everywhere that it's going to match. So backslash B again means, whoops, at a word boundary. That's at a transition between a word and a non-word. So a non-word could be start or end of a string, white space of any kind. So basically anything that's not considered a word when it transitions between the two, going either direction, either from a non-word to a word or from a word to a non-word. That's what B will match. And again, I think there was a lot of confusion last time, so I thought I would go ahead and run through an example so you can see how it actually works. Okay, so it's saying starting, and it's testing to see if it's at a boundary. And it said, yes, that's a boundary. So start of string is considered a boundary between a non-word and a word. So it's looking for the literal sequence, matches that. Then it's testing to see if we're at another boundary. Yes, we are, because we're going from a word to white space, which is a non-word. And then again, going through it. So you can see us transitioning each way. Does that make sense to everybody now when you see it actually run through? I love RxRx so much in giving these presentations because I realized through this one, I was going to use it a lot more than I used it in the first talk, so you can actually visualize how this stuff works. Because it's amazing I talked about this in the first talk, but it's really amazing to see how much backtracking goes on in regular expressions that you don't normally think about. They usually end up doing a lot more backtracking unless you're doing something really simple and straightforward. It ends up doing a whole lot more stuff than you think it does. Yes?
If the first character of a string is a non-word
Yeah.
character, does the slash B still match the beginning of the string?
Yes. That's what it just did. Is I had one at the beginning of the string.
We had a word character at the beginning, but I'm wondering if we had like a space at the beginning.
Oh, that's a good question, actually. You know what? Let's find out real quick. I'm going to do what you're never supposed to do. Whoops, hold on. Wrong place. That's why you're never supposed to do this, because you end up doing it wrong. All right, we'll rerun this. Did I describe what you were asking for? Or did I do what you were asking for or not?
No, not quite.
I think it's still a match because there's no anchor on the left. So.
Yeah, so it's still going to match even though it failed matching the first space, but it's still as soon as it hits the transition between the white space and the D. So what were you asking for again? Try again
I was
and see if...
asking the slash B, so the slash B in this case didn't match the beginning of the string. And I'm wondering whether the slash B will match the beginning of the string in a case where got a non-word space. Yes, slash B space.
Well, if you
slash
put a
B
caret in
under-
front maybe of the slash B,
Oh.
I think maybe that's what you wanna know.
So you're saying two backslash B's here
and just put a space between.
and have a space between them.
That's what I wondered.
Okay. Let's go ahead and find out. Okay. So that failed. Then it succeeded there. Now it's going to fail on the space. So it looks to me like no, it's going to bomb out. This is what I love about this so much is you can just go what if and try it and see what it does. Well, because the first backslash B was between the beginning of the string and white space, both of which are considered non-words. So that's not a boundary. And then the one afterwards did match because it's a space and a D, which that is a boundary. But the problem is, since the first match, part of the match failed, it just threw everything else off.
You never would
So.
use consecutive backslash B's then.
Yeah, I can't even think of any way that would.
There's a space in
Oh,
between.
that's right, that's right, there is a
But
space
even if you
there.
have
Yeah,
consecutive.
I don't think the issue's not consecutive.
Yeah, it's not going to work because you can't. You're basically backslash B's are matching in between characters, and you can't have two in betweens in between two characters, you see, which is what backslash B would be.
And backslash capital B is matching a non-boundary.
Exactly. It would match in between the D and the O and the U and the G because those are
And you know,
non.
two backslash B's together might actually match because both of them, since they're zero width, right?
Yeah.
Both of them are at a boundary.
Oh, that's,
So it
well,
might actually match.
all right. Well, we'll go ahead and try it and find out.
And get rid of the space and the, well, I guess it doesn't matter, does it?
Okay. We'll try it with space
Except for the
first.
anchor there, so.
I like how RxRx knows that I'm using full debugger, so it allows N to step through.
Did it say assertion failed or no?
Yeah.
First one failed?
Okay.
Yeah.
No, you were right. It did succeed because it's zero width. So, okay. Well, we all learned something. Okay, we can go home now. All right. Yes, capital B. I'm not going to go through that one. Capital A, and especially lowercase z, are basically almost synonymous with caret and $sign. The only difference being that those are not, their behavior is fixed. They always behave the same way regardless of what flags or modifiers you throw on the regular expression. As we saw from previous slides, basically, if you're using M or S, you can change the way those behave. But basically, if you just always mean the beginning of the string and always mean the end of the string, regardless of what flags I've got on it, then that's what you want to use. And this kind of came up, Dave and I were having a discussion about it because it was in Perl best practices to use these. So anyway, we were just talking about that earlier. Okay.
Big A and little z would be if you were reading it like a whole page of a book.
Sure, something like that. And you truly wanted to anchor at the beginning and the end.
Everything in between.
With, let's say you might have an M flag on there, but you still want to match at the beginning and the end. So yeah, that's how you'd use it. Okay, backslash G is very important. We're going to be seeing that a lot throughout the rest of the talk. That matches at whatever POS or position, and basically position takes a string. Every string in Perl has an internal pointer so that when the regular expression, as you can see when we step through it, you see that arrow, that's indicating where the pointer is that it's keeping track of. When I say pointer, I'm not talking about like C pointers. I'm just talking about an index pointer that keeps track of where it's at in the string. So if you use the POS function, it will tell you, it will give you a number that tells you what position that it's at currently for that string. And so we're going to see, that'll make a little bit more sense later. So it's basically at the end of the match of the previous global search. So you remember how we had the look ahead? And I said, hey, that's going to save that for another regular expression. Well, this is why. You can use the \G to say, hey, start where the last one left off, which in our case would have been friend. Do you remember how it didn't consume friend? It actually backtracked and said, okay, I'm going to start at this point next time. Is that cool with everybody? Make sense? Okay. All right. Now I'm just going to talk a little bit about some things I touched on in the last talk and some things I didn't have time to cover at all. We'll see how I'm doing since we went off and started experimenting. Okay, so capturing parentheses, basically just take by count. So however many parentheses you have, you just count them out. And it will match. If it matches, then inside of $1, $2, $3, you'll have whatever it matched. We kind of covered that last time, so that's not too new. Alternation, I didn't cover. Basically, alternation is similar to a logical OR. It's saying if you've got this thing or this thing or this thing, it matches. I don't care which one it is. And I'll go ahead and run an example. So you can see there, hello world and hello world matches. It actually, I'll show, instead of explaining it, I'll just show you in the program. I'll bring it up first just to show you what it looks like. So we've got the string hello world, and the regular expression is hello space, and then non-capturing, just grouping, foo bar world class. So if we've got foo bar world or class in that string after hello, we're good. So I'll go ahead and run that. Okay. So matched hello right away. Matched a literal space. Starts on the non-capturing group. Tries foo, says no, no foo. Tries bar, failed. Says world, okay, we're good. And so you see it skips class because there's no point. We've already found a match. We don't really care which one matches. So again, it has short-circuiting behavior like you normally expect ORs to do in conditionals. That it just says once one thing is true, I don't care about the rest. I don't even have to check them. And it does the same thing in a regular expression. So we good on alternation? Okay.
A quick question, you're
Sure.
capturing, are you gonna go into how you assign the dollar number, match it up to the parents? Like, what if you have nested groups?
It's,
So, I mean, just cover the rules.
yeah, actually, I kind of talked more about that in the last presentation, but it's basically, I believe, in one of you guys can correct me if I'm wrong, it's counting from the opening parenthesis. So it's like if you've got nested, it counts from the opening parenthesis will be the number of it. If we've got time, maybe I'll sling up an example later.
Cover that or not last time.
Well, I did talk a little bit about the numbering, but I don't think we talked about nesting. So maybe if I don't have time, I'll whip something up and send it out to the mailing list later. Just shoot me an email to remind me if I don't. Okay, and then grouping, which we just saw in our example, is we've got grouping without actually capturing. So there's nothing in $1 after that match. Most of the time you'll want to do this. There's no reason to capture if you don't care what the value is. You just want to group things. Then use the grouping parentheses rather than the capturing, because there's no point in capturing something you're not going to use anyway. So if you care and you want to keep it, capture. If you don't, use the non-capturing.
I guess according to what he just said, if you had hello world, and you had two parentheses around hello world.
Yeah.
And inside that, you had parentheses around hello, and parentheses around world.
Okay.
Would you get
Well,
$1?
that's a good example. We'll keep that in mind, and I'll try to keep on time enough that we'll actually try that at the end and see what happens. See if we can divide by 0 or something. Okay, look around assertions. So this, we've already seen one, and I'm going to go ahead and show you the other ones. This is the positive one, which we've already seen. Basically, in each one of these examples, I have a succeeding example and a failing example to kind of give you a feel for how it actually works. So we've got foobar with a tab following it, and the regular expression is word, one or more word characters, followed by the parentheses, question mark, equals means positive look ahead assertion, 0 with positive look ahead assertion, which means look to see if it's there, but don't consume it, back up and leave the pointer in front of it. And then our next example is taking foobar and replacing the tab with a new line and then doing the same match. So I'm going to go ahead and run it so we don't have to guess what it does. We'll just look at what it does. So it looks for word right away, matches foobar because it's all word characters. And then it's starting the positive look ahead, looking for a tab character, which it did. It matched. And now it's backtracking again because it doesn't want to consume it. And so now you can see it consumed foobar, but the tab is still there. And so the pointer is still pointing at the tab character. Normally, if you didn't do this kind of a construct and just had the \t there, it would have gone all the way to the end of the string. Just want to make sure everybody's clear on the difference there. Okay, now we'll go into the failing example. So now we're looking again for word, one or more word characters. Foobar does match. Starting, looking for a tab. Nope, no tab. We got a \n. And so now it's going to do some backtracking and keep trying and trying and trying. And, oh, this is one. I'm going to just hit continue because some of these try really hard. So I'm just going to let this one go. So you can tell it took 101 steps for it to figure out, hey, there's no possible way that this can match. So that one ended up failing. Is that clear to everybody? Positive look ahead. That's going to be the most important one because that's the one I've got a full program example of using.
This is supposed to be a variable length expression.
Yes. Yeah. Okay, so 0 with negative look ahead assertion is saying I want something that's not followed by something else. So that's why it's negative rather than positive. So we've got foo_bat with foo negative look ahead, 0 with negative look ahead assertion bar, and then foo_bar, and then boom. So again, instead of hand waving, I'm just going to run it. Okay, so foo's going to match right away. It's going to do a negative look ahead. And it says, yeah, there wasn't a bar afterwards. So it literally, it didn't matter if that was bat or if that was abracadabra or supercalifragilisticexpialidocious. It doesn't matter what was there. As long as it wasn't bar, then it would successfully match. Does that make sense? Okay, now we'll go on to the failing case. So it's matching foo. Now it's looking ahead and it matched bar. And so, but it wasn't supposed to match bar. So even though it matched, it backtracks now because it says, oh, I wasn't supposed to have foo there. I'm just going to hit C for continue to let you see it go. Then it just backtracks and then just goes single character all the way through. It says, nope, I can't do this. I can't make it work. Make sense? All right. Okay, this is a zero width positive look behind assertion. Now, positive and negative are keeping their same definition, but now instead of looking ahead in the regular expression, now we're looking behind the pointer where it's already been. So the example I have here is for a positive, we're looking for a word character that's preceded by a tab. Does that make sense? Because that's what this construct is with the parentheses, the question mark, the arrow, and the equals. That's saying, I want to look that way. That's what the mnemonic kind of is saying, I'm looking behind. And the equals is saying positive. The exclamation point, as we'll see in the next one, is saying negative. So, and then down here, I'm doing a similar trick that I did the last time. I'm just changing the tab to a new line, and that one should fail. But of course, the most interesting part is actually seeing it run. So it's starting here. You notice right away it didn't match there, and then it did match once it was in the tab. And now it's looking for word characters, and there you go. But the reason why this is red is because that was, even though this was consumed in the point, in as far as the next regular expression, the pointer's not going to be here. It's because it's already past that point. There are some special variables in Perl that store what was before I matched, what did I match, and what was after I matched. This will get left out of what was before I matched because of that. That's the function that this serves. But I can tell you that I have never, ever, ever used a look behind assertion for anything. So they're obviously there for a reason. I don't know, either of you guys, have you ever used a look behind? No. I have used look ahead quite a bit. Sometimes for a very specific purpose that I'll show you, and then I've used them for other reasons, but I've never used the look behind. But just for the sake of completeness, I'm going through it all. So now we're going to try it with the new line instead, and it's going to fail. And it's trying again, and it's failing, super fail. We'll hit C and just let it go all the way through. And it just gives up. Can't do it. All right, so far so good? Makes sense? Okay, last one. And if you memorize these names, you can amaze and impress your friends or make them think you're a real dork. Zero width, negative, look behind assertion. Anyways, okay. So now you can see the construct is basically the same, but we've got an exclamation point there. Oh, you know what? You're right. Thank you. Yeah, because the arrow was missing. Yep, I was just noticing that. So I got to fix that in my slides as well. Thank you. That's what I get for doing this at the last second. All right, there we go. That's better. So now we've got the arrow that says, yeah, look behind, but instead of the equals, we've got the bang, which says nope. So now we've got, again, a very similar to the other example. This is saying I want something, I want foo that's not preceded by bar. And so we're going to match it against these two strings. This one will succeed, this one will fail. Thanks for catching that, Greg. Because I was just about to, when you said that, I noticed, I'm like, where's the arrow? Yeah, cut and paste error when I was doing the slides. Okay. So we're looking at the negative. Now it's looking for foo. Says, nope, failed. This one, it's got to kind of go a character at a time because it doesn't know where in the string foo's going to be. So it's got to keep looking until it finds foo, and then it's got to figure out what was behind it, if that makes sense. So you see how it kind of steps through one at a time until it hits foo, and then it goes, oh yeah, everything is all good because I hit foo. So, but again, this is left out of that special variable, which you can look those up if you want. I'm not going to go into those special variables and what they all mean. Because again, I've only got an hour and way too much stuff to cover. Okay, this is our fail. So again, it's having the same thing. It's still looking for foo, and it can't really make up its mind until it finds foo. And now it's starting to backtrack once it hit the foo, starting to backtrack and say, hey, I don't really know what to do with this. It failed because it started with bar and it ended with foo. There was no way it could succeed in its match. All right, does that one make sense? Okay, those are all the look around assertions I'm going to cover tonight. So, all right, now we'll get into, I think I should have enough time for this, a practical example, which I didn't do much of in the first talk. It was more just, this is how everything works. Now I'm going to show you an example of why would you want to use this kind of stuff? What kind of things can you do with it? So, first of all, this is the template that we're going to be parsing. So it's going to go through this, and as you might imagine, these little tags have special meaning. All arbitrary. I just made this up. You could be angle brackets, percents, or whatever, as you see in other languages, or ats, or whatever. That's just what I'm using arbitrarily. And you notice it's got a single word inside of each tag. And so now we're going to go through and run it, see what it does, and then we'll go through the code. So this is all this text is hard-coded in the program. In real life, you wouldn't do it this way, but again, I'm just trying to make a simple example here. So it just puts in a title, it puts in a header, and it puts in the current year where the tags used to be, right? So we've gone from this to this. Everybody follow that? You notice we've got no tags left. They were all replaced by something. Now we're going to talk about what they were replaced by and why. Okay, I am using IOAll. If you're not familiar with it, don't let it mess with your head too much. I find it useful for input-output that's a little simpler than opening and closing files all the time. So first I just get the template file name, which you saw or you may have seen when I typed it on the command line. It's simpletemplate.html. So I'm just pulling that in. Next line is we're creating an IOAll object. This is a slurp. Don't worry about it too much. It's not the purpose of the talk. So basically it's just reading in everything that's in template and putting it all into a scalar, right? I realize the syntax is not syntax you've probably seen before, but that's IOAll. So then I use quote meta. What's good about quote meta is that it will take whatever string you have and properly quote it to be used as part of a regular expression. So if there are any things like the square brackets, you remember those are meta characters. We talked about that in the last talk. Those, if you want them to be used as literals, they have to have backslashes in front of them. So this will take care of all of that for you without you having to remember, oh, what do I have to backslash and what do I not backslash? So takes care of all that for you. Then basically I've got a hash here with, you notice these were the names of the tags. So I'm just mapping the names of the tags either to a string literal or to a reference to a subroutine. And I'll give you, spoiler alert, I'll tell you before we go through the details of how it works, that's all it really does, is it runs into a tag, says, okay, this is the name of the tag, looks it up in this hash, and replaces it with whatever's here. If it's a tag it doesn't recognize, it's going to just say, I don't know what to do with it. And I think, I'll have to test it, I can't remember. This is basically a program that I stripped down from a real program that I'm using. So I just took this and made it as simple as possible. So I can't remember what it's going to do if you have a tag that it doesn't recognize, but we can try that. And I can't remember if it leaves it alone or replaces it with nothingness. We'll have to see. All right, everybody good with that so far? Make sense? All right. So now we'll start to get into some of the details. Line 25, I've got a position stack that I want to keep track of. And then I'm deliberately, position is one of those functions in Perl that you can assign a value to. And basically, it's just to suppress the warnings because position on a string that you haven't matched against yet, it's really undef. It's not zero. But in Perl, undef 0, who cares? So I'm deliberately setting it to 0 just so it doesn't give me a warning that I'm trying to use an undefined value. That's all. So that's, if you didn't have warnings turned on, you wouldn't even need that line. It would work fine without it. So now I'm going to, this is the main loop. I'm going to say while the position, you remember, and the position is the pointer that's internal to the string, is less than the length of the total string. In other words, it hasn't reached the end yet. While it's still somewhere in the middle, keep doing all of this stuff. So the first part of all of this stuff is look for a start tag. And you remember the start tag is this right here, right? And the end tag is that. So we're looking for \G start tag, which is, going to be a backslash, open square bracket, dash, dash, followed by white space, one or more. And you notice I have a G and a C. You remember the G is global, right? So it's going to do it as many times as it can. The C means if this match fails, don't reset the pointer to the beginning, leave it where it is, even if it fails. Now the interesting thing is, since I'm doing this in a loop and I'm just doing this in a scalar context, the global isn't going to match through everything all at once and return it all at once. It's just going to go through it one at a time. And especially with the backslash, that's in conjunction with the G, the C, and the backslash G. So currently, backslash G is the start of the string, right? You remember we talked about that earlier, because that's where the last match was. We haven't done a match yet, so it's at the beginning. Backslash G is at the beginning. So it's going to look at that. I'm not going to step all the way through it, but I'm just going to point out that would be at the open angle bracket on HTML, right? And it's going to fail because there's nothing that looks like a tag there. So it's going to skip all of this stuff. Let's say though what's going to happen when it actually hits this start tag. What it's going to do is mark the position, save that off, right, using the position function, and then that's going to be where the start of the content is, because it consumed all the way to the end of that tag. So the square bracket dash dash, that's where the pointer is, right? So that position we're going to keep track of. And then we also want to keep track of the start of the tag position. So it's basically the length of what was just matched. And what was just matched was the start of the tag. So I'm just doing a little math to count backwards because I want to keep track of both the start of the content between the open and close and the start of the open and the end of the close. Does that make sense to everybody? That's almost a whiteboard thing, but actually, you know what? I can do it this way. So I'm keeping track of this distance and this distance. Well, actually not with minus the white space. Does that make sense? So I want to keep track of the length of the whole thing. I want to keep track of the length of what's in the middle. And we'll see why later. Okay, so if this didn't match, which in this case, if we're starting at the beginning of the string, it won't match, it's going to check next for an end tag. And again, since it's angle bracket at the beginning of the string, it's going to fail. But let's pretend it hasn't failed, and it's matching this right here, okay? What it's going to do is pop off of the stack. Oh yeah, sorry, I skipped this line, which is very important. I'm pushing on anonymous array with both of those positions and the reason why I'm using a stack is because I'm going to show you in another example, these tags are nestable. You can nest them inside of each other to infinite depth. So every time it hits a start tag, it's going to push something on the stack and keep track of all the positions it needs to keep track of. Every time it hits the end of a tag, it's going to pop something off the stack. And those, as long as your open and closes are balanced and matched, then it will always match the correct numbers with each other, the correct starting positions and the correct ending positions. So far, so good? Haven't lost anybody yet? Okay. Hopefully it'll make more sense once I get all the way through it, because I know that parts of this are kind of fragmented until I put it all together at the end. All right, so first it's going to pop off the start position. Then it's going to do the same thing we did with the start tag. It's going to just grab the positions. So the end position, now the pointer is at the end of the dash dash close square bracket. So we just take that. And now we do the math backwards to, again, match the end of the length of the contents inside. So it's the middle. So we're grabbing the outer part and the inner part, and we're keeping track of both of those numbers. Okay, so now we're going to actually do something about it because we're at the end of a tag. So now it means, hey, we've gone all the way through this tag. Let's do something now that we've hit the closing bit of the tag. So now we can figure out, well, how long is the total tag? Tag end position minus tag start position. And then how long is the content? It's the tag content end position minus the tag content start position. And then what we're going to do is take the template content, take the start of position of the content and the content length. What that actually means in real life is it's just going to grab this right here. So that's why I'm keeping track of all those positions, is because I need it to grab pieces, and then I need it to, it's going to actually replace pieces. And when it replaces it, when it grabs it, it only cares about the middle part, doesn't care about the opening and closing parts. When it replaces, it does care about the whole thing. So that's why I got to keep track of both sets of numbers. Okay, so we do that substring, we grab it. Basically, it's going to have whatever first word is there is the name of the tag. Whatever comes afterwards, if anything, in this case, we don't have anything in any of those tags that come after. But if there was, in the next example, there will be, it's just treated as parameters, and it's just passed to the subroutine that's called to handle that tag. So again, this doesn't matter this much for this example, but for the next one it will. Okay, so now it's going to actually do something. So it's going to pass the tag name and the parameters to handle tag. So we just grab tag name, parameters, and we set up a variable to hold the content. So now I just check, again, you remember our hash we set up at the top that had either string literals or references to subroutines. And so now it's going to determine what is it do I have. If the reference is equal to code, that means it's a reference to a subroutine. So that means what I'm going to do is use that reference, anonymous reference to a subroutine, pass in the parameters, and whatever it returns is going to be my tag content. I'm going to go back up to give you a concrete example real quick. Let's look at year, because that's the simplest one. All the subroutine does is return the fifth element of what's returned by local time plus 1900, which if you know how local time works in Perl, it returns the offset of the year based off of 1900. So that's all that's doing, is figuring out what year is this, and it's just returning the year. Does that make sense to everybody? So literally what this is going to hold afterwards when it hits the year tag is 2013. Otherwise, it just assigns itself to whatever the string literal is. So the first two, like the title, tag parser example, and the header, this is a header. So see, there was our title tag parser example, and this is a header. And this is where the year was. Is that kind of starting to put everything together for you? Stop me at any time if you have questions. So, all right, we've handled the tag now, and we've returned some content. But now we've got to go back and actually replace that in our original string, in our original HTML. So this is the substring that does it. So it takes the template content, which again is all of the HTML. It takes the tag start position, the tag length, which we calculated because we had the start and the end position, and then the tag content, which we just got returned. And what this 4 parameter version of substring does is takes this content, starts at this position, goes for this many characters, and whatever is here replaces it. So it replaces the word title with the actual string, whatever it was, tag parser example, or this is a header. Or in the case of year, it replaces the word year with the start and end tags with 2003. All right, now what we have to do, and this is something, if I remember right, I wrote this code years and years ago. Well, not this particular code, but the code that this was derived from, is you have to recalculate the position because now you've just you may or may not have changed the length of the string, right? If the tag is tiny and you replace it with something long, well, now your positions are all out of whack because you remember we're already at the end of where that tag was, which may be in the middle of the content you just replaced it with. So that's not going to be any good because we don't want to start in the middle of that. So they could be the same, but in most cases they're probably not going to be the same. So we recalculate it. So we take the tag start position plus the length of the tag content, which was what we replaced it with. And we say, now that's the part that you start at. Does that make sense to everybody? I know it's a lot of math and a lot of numbers to juggle around. Yes?
You mentioned that you can nest the tags, so wouldn't you want to start back at the start tag position to see if there was a nested tag in there?
Well, that's a very good thought. And actually, I just briefly had that thought, even though I know it doesn't work that way. So I'm not surprised you had that thought. The reason that doesn't happen is because all of the action is when it hits the end tag. Since the tags are nested, it's going to hit one open tag, another open tag, a closed tag, which is going to handle that tag, and then another closed tag, which is going to handle the whole thing. Now, if you, instead of nesting them, if you intersperse them, it's all going to blow up. It's not going to do what you want at all.
The results of one tag to return other tags, you would want it to start back at the start position.
Yes, that's true. And actually, the code that this derives from does that. But again, I was trying to keep this simple. So you're absolutely right that if you did want tags to return tags, which I actually do in real life, so I actually do that, you would, instead of putting it at the end, you would subtract it to start back at the beginning and reparse everything you just parsed. I was just trying to keep this conceptually simple. The math is really no more complicated, but I just wanted to keep the concept similar. But that's a good point.
Do the whole thing with just two regular expressions and looping through the keys of the hash. One regular expression to capture the entire tag with a capture variable on what's inside. Then do the lookup in the hash, and then the next one do a substitution, and they just loop through all the keys.
Well, the problem with that is the nesting. The problem with that is the nesting. That's what this buys you is flexibility. If you didn't want nesting, and you also didn't want, like Greg was saying, you didn't want tags that can return other tags or maybe multiple other tags, then you could do it that way. In fact, just out of curiosity, I actually ran some NYT profs against this, just doing search and replaces, just with the substitutions. So much faster to just, even though you would think, I even tried it with big HTML, much, because I figured, small HTML, maybe it, that factors into it. Even with huge HTML, it's actually much, much faster to just do a search and replace, search and replace, search and replace, even though it starts over and parses through the whole string each time. You would have to, I would guess, get just immense, huge amounts of text before it becomes more efficient to do it this way. So this is definitely less efficient, but more flexible. But big surprise there. That's how programming works. So, all right, we're on the home stretch here. Else, you remember our first condition is start tag, second condition is end tag. Well, what if it's neither? Which a lot of that junk, actually most of that junk is neither. We've got a bunch of HTML. So then what it does is we're doing a regular expression match, again, anchored by the starting position, \G, followed by one or more of anything that's not greedy, because you remember the question mark afterwards makes it not greedy, followed by either, and this is a zero width positive look ahead assertion, because again, if I find a start tag or an end tag, I don't want this regular expression to handle it. I want one of the other ones to, right? Because if I handle it here, we've now passed our start tag. And so when we loop back through, it's going to skip over the part that I wanted to handle, the start tag, pushing all the position numbers onto the stack. So that's why I use this here. Now, way back in the day when I started with this code has evolved over time. I wasn't nearly smart enough to do this, so I was just doing position of that plus 1. I was just basically incrementing the position character by character. Hugely way more inefficient than doing it this way, because this way the regular expression can skip a whole lot of junk, and I'll go back to the template and show you how. So it's either a start tag or white space followed by an end tag, or our friend \z, the actual end of the string. So what that regular expression is doing is that's the part that's handling all this crap. It goes zoom, 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 zoom. Oh, hey, I matched this, but I have to back up and not consume it. And so then it backs up. And then that way, when it loops back through again, it goes, oh, hey, I'm at a start tag. So then the start tag stuff does its calculations. Then it'll keep zoom, 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 zooming through here until it hits the end tag. And then it goes, oh, end tag, pop off the numbers I need, do all those calculations I need, and then actually replace this whole thing with whatever title tells me to in the hash. Does that make sense? Then once we're done with that, we're recalculating the new end of it, which is somewhere over here, right? The new end is over here rather than, you can tell the tag is a lot shorter than the text I replaced it with. So then it's going to zoom, 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 zoom all the way through to here and then back up because of the look ahead and say, oh, I'm going to start there. So we're actually done with the program. Does that, everybody kind of have a handle on how that works? Does that make sense now? Okay, now I will show you some nesting, which is why we're going through all of this headache here. So I created a new, again, the syntax is terrible. I just made this up as I was going along. So we've got a new tag called upper, and it can contain other tags. And basically, again, spoiler alert, it's going to take whatever text, title, and header spit out and convert them to uppercase. And I'll go back to the code and show you that. First, I will run it, just so you can see I'm not lying. So now you can see it did basically the same thing and just converted all to uppercase. So this is what I'm talking about. This is where you're starting to see the flexibility of doing it this way rather than doing it the other way. Which, again, if you don't need this complexity, then don't do it this way. Do it the simpler way. But for my application, what I needed this to do, I needed to be able to have basically infinite nesting and infinite processing of any tags that get returned to get reparsed. And actually, Greg, you make such a good point that I'm kicking myself now that I should have left it the other way and just done the math that way, now that I think about it, because it's not really conceptually that much harder to understand, I don't think. So anyway, so I oversimplified. Okay, so let's go back to the code and we'll just see. I'm not going to go through all of this again. I'm just going to show you what happens differently. Okay, first it's going to go zoom through this and stop here, right? Then it's going to grab this and stop here. Although actually we're not consuming white space either, so it's actually just going to grab that. Right? It's going to stop here because we've got another open tag. So we don't want to, we stop, we say we don't want to process that, and we push everything onto the stack. Well, we haven't hit an end tag, and you remember end tags are where all the action happens. All we do in the start tag is do some calculations and put them on a stack. So now we zoom ahead to here, go, oh, start tag. So we do some more calculations and push those on the stack. So now we've got 2 sets of calculations on the stack. Hits this title and just keeps right on going until it hits the end tag. Then it goes, oh, okay, I've hit the end tag, so it pops off the calculations that we did for this tag. Then it replaces this whole title with the string that it replaced, right? Okay, so now what it does is it zooms. This has now been replaced. We've recalculated our position and everything. Everything's good. Now we hit this end tag. Well, now it's going to call upper. And what does upper do? It takes one parameter, just called string, and says return UC string, uppercase string. So it just takes the whatever string it gets passed and uppercases it and returns it. Nothing fancy. Again, the point of this was I just wanted to keep it simple. So now let's go back to where I was talking about that it wasn't important, and now this is important because now we've got the word upper, right, which would be matched by this. Then we've got white space. Then the whole rest of that is, in the case of the title, this text, right? Everybody with me so far? So this text is now going to be the parameter, even though I say parameters, but it's actually just one parameter. It's going to pass it down to handle tag, and now it's going to be passed to this subroutine. This anonymous subroutine is this up here, and so it shifts that off, that parameter off, which is the text, and it returns it uppercased. And that's it.
At that point, when you extract the argument parameter,
Yeah.
it has already been substituted by the previous nested bunch of
The internal tag has been, yes, the internal one, yes. So basically, what it does is because of the stack, it just keeps going and going and going and pushing things on the stack no matter how many nested tags you have. And then it's going to process them from the inside out, right? Because the first end tag it's going to hit is going to match the innermost start tag. So once it hits that first end tag, it processes that. Then it's going to hit another end tag. And so then it processes whatever was returned by that plus what was already there. And it will just keep doing that on and on and on. So, any questions? I guess I went over a little early or a little late here. Or everybody good with that? Okay. Actually, I'm going to do something here real quick. Whoops. I'm all screwed up because the stupid system made me change my password today. The system here at work, so now I'm thrown off on all passwords on all machines for some reason. Let's see. Oh, well, let's look at my solar because I've talked about that before. I haven't looked at this in a long time, so I have no idea what this is going to look like. Again, this is why you should never do this live. And it's also taking an incredibly long time to come up. Yeah, I'll save it for later. Maybe on the mailing list, I'll mail out an example of how I actually do this. And the syntax for the tags I use is actually way more involved than this very basic. Oh, okay, good. So you can see here, I guess it's not, can most people see this? So I can have variables in here, and basically key value pairs are my parameters. So I've actually got extra parsing in there to parse out the key value pairs. And then I can just use variables here. Let's see if I've got, oh, here we go. Like here's an SQL query. So with that parser, you can do all kinds of really complex things if you just add a little bit more flexibility to it, like what Greg was talking about, and some extra parsing of the internals of the parameter. And as I always say every time I talk about this templating system, in my defense, when I started this like 15 years ago, there weren't a bunch of templating systems around like there are now. And yet I persist, just, I don't know, I need a hobby to keep me out of jail. So anyways, that's it. Thanks for coming.
Can I, it'd be interesting to take a look at what happens with the result variable for your SQL select. That was very interesting.
Oh, yeah, basically what it does is, yeah, that's way too much code to try to show you, so I'm just going to explain. Is what it does is it stores the STH, the statement handle, in it. Yeah, exactly. DBI just gives you the statement handle, which you can use in a later tag, because what it does is, even though it looks globally, oh, I'm sorry, you can stop anytime.
But
I'm
if
just
you wanna
talking.
cover real quick the nested parentheses or wait for another time?
I think I'll do it on the mailing list,
Okay.
because we're already like almost 15 minutes over, so
Okay.
just so everybody can get out of here.